Hello everyone. In this video, I'm going to present my undergraduate thesis, which has been done on seismic performance of bridge substructure designed as per AASHTO code. First of all, I will provide a background of the study. So, Bangladesh is a riverine country, and as a result, a lot of bridges are there over the rivers. And besides, Bangladesh is also an earthquake-prone country, which have fault lines in the north and east direction of Bangladesh. As a result, there has been a lot of earthquakes going on after 1980s. So, design according to the earthquake resistance of the structure is necessary. But at present, there is no specific code for bridge design which includes the seismic effects. So, as a result, people I mean the designers use the foreign codes like AASHTO. So in this study, I am trying to provide a guideline, basically a procedure to design the bridges for earthquakes while incorporating the BNBC parameters to the AASHTO 2020 parameters. I will first go through a literature review. So the earthquake design philosophy, which is already known to people, which is a very widely popular philosophy, is that we will design the some members to be to be of less strength but with a higher ductility. So they will absorb the energy through ductility other than the strength. So what we'll do is that we will not design the structure for the elastic design force. I mean, we will not design the structure such that it will be remaining elastic even during the maximum considered earthquake. In that case, it will be very uneconomical. So we will actually provide some closely spaced syrups at the ends of the elements so that they take some extra values after their yield point, so that we can achieve ductility and thus absorb energy through the ductility. BNBC 2020 provides 4 seismic zones and the specific PGA values are provided in the map. However, AASHTO 2020 has different type of seismic zonings, and that's why we need to take the BNBC hazard parameters and implement them to make them available, to make them accurate for our country provisions. So what we'll do is that we'll take the PGA and other values from the BNBC and we'll incorporate in the AASHTO 2020. So the soil classification will be done based on AASHTO 2020 provisions, and the response spectrum that will be generated will be also based on the AASHTO 2020 guidelines. Now the design and detailing guidelines will also be according to AASHTO 2020. So for different zones, AASHTO provides some guidelines of what reinforcement will be provided, what the spacing of the reinforcement will be provided in the end regions. So we'll conform to that, and after that we will do a nonlinear analysis to check whether during the seismic conditions the structure remains within the performance level. The performance levels has been shown in the slide. Now we'll move on to the design of bridge substructure. The bridge we are considering has been shown in the slide. It is a bridge on the osteogram that has 2 lanes. The span lengths are 40 meter, and it is situated in the seismic zone 4. That's why in the high severe seismic zone. We are not actually modeling the bridge or designing the bridge as a whole. We are designing the substructure, and as a result we are not providing any slabs. We are transferring the loads from the spans to the bend cap, and then that will be passed through the piers and then pile cap and to the piles and to the soils at last. Now the model as the single pier bridge modeling has been done in this way, and these are the parameters that we are considering for the modeling and designing. Then to determine the demand, we are using a factor of 0.8. So basically AASHTO 2020 has the provision of design basis earthquake which has a return period of 1000 years, but in BNBC 2020 the return period is 475 years. So if we use the same factor, which is 0.67, for converting MCE to DBE as like BNBC, then it will not be actually okay. So as a result, we have to use a factor which is higher than the 0.67, and according to the geotechnical judgment and the literatures, we are providing a factor of 0.8 to convert the MCE to the dBE, and the seismic parameters has been generated according to the factor. This is the soil that we are considering for the soil structure interaction. So the piles are actually underneath the riverbed. So as a result, there is a significant portion of unsupported height. So, and for that we need to actually check the performance. We need to actually model the soil structure interaction, and for that we need the soil values. This is the soil data, and the nonlinear soil modeling has been done. The PY curves, which is the lateral load versus resistance curve, load versus displacement curve, sorry, that has been generated according to the API guidelines, and the TZ and QZ curves are generated according to the AASHTO 2020 guidelines. The 3D model that we have done in this app has been shown. Now regarding the pier design, AASHTO 2020 provides some response modification factors according to the column numbers, and also the occupancy category of the bridge. So according to that, the response modification parameter for single column on the other category bridge is 3. So which means that the piers need to be designed for a reduced force, that means the elastic design force divided by 3. But for the piles, AASHTO 2020 provides two options. You can either design it for the elastic force, or you can actually design it for the hinging force, but we don't know the hinging force. So one of the objectives of this study is to actually provide a guideline to the hinging force, so that we don't have to design the piles for such a higher elastic force, and instead we can actually design that for the hinging force, which is a much lower force. So first of all, we designed the piles according to the elastic force, sorry, but the piers are designed for the reduced force, which is according to the response modification factor. So the design of pier, the detailing of the pier has been shown. Detailing of the piles according to the elastic force has been shown here. And then we turn to the performance evaluation. So for the performance evaluation, firstly we use the hinge types. So according the hinge, what we mean by hinge is that when a real life earthquake will be occurring, like a very strong earthquake, in that case the structure will not remain elastic. But as concrete is very brittle, so to make it actually ductile, what we do is that we provide closely spaced stirrups at the end regions. Mostly the joint of the pier and the pile cap, that will be having a lot of movements, and that's why we will provide hinge at that location and also to the pier top. So the hinge definition has been taken from ASC 4113, so which provides a backbone curve as shown in the slide, and also the specific values of A, B, and C, which actually define the hinge properties. So when we actually provide the reinforcements in the section and then we assign the ASC 4113, it automatically calculates the values of A, B, and C. This has been already said. Now we conduct a pushover analysis. So for the pushover analysis, we first actually use a gravity nonlinear loading, and after that we assign the pushover analysis. So in this pushover analysis, we provide a loading which will be an acceleration loading to simulate the earthquake behavior, but it will be a static load. As this is a static pushover analysis, this will be a static load. So that means that the force will not actually vary. It will be a same level of force. So in this slide, you can see 3 different gradual hinge formations under lateral loading, and you can see in the last point, in the last figure, that even after the formation of the hinge crossing the CP limit, there is no hinge formed in the piles. Although we had provided hinges in the piles also, but no hinge is generated in the piles because we designed the piles for a much higher force, and that force actually never actually occurs in the structure. So this is the pushover curve that we found from this software, This is the pushover capacity curve. The dotted line that has been shown here is the MCE demand line. So there is a convention for getting the for evaluating the demand displacement for the bridges, is that the displacement that will occur to the linear structure will be same to the displacement that has been occurred to the nonlinear structure if they are designed for the same load. So from that we can actually say that the dotted line actually provides us the demand capacity, so sorry, the demand displacement. And from the pushover capacity and the hinge limit states we can find the different performance capacity limit states like immediate occupancy, life safety, and collapse prevention. And we as this bridge is designed under category other, so the criteria for the performance here is that the structure has to remain within the CP level in the maximum considered earthquake. So we can see that the capacity of our capacity is much higher than the demand. So in this case we can finally conclude that our performance is doing okay. Now another main objective, as we have already said, another main objective of this study was that to find the overstrain factor or the hinging force. Now the hinging force is the maximum force that will occur to the specific elements. So if I talk about the pier ends, in the pier end the maximum moment that will be occur in the pushover analysis, if we divided that by the design moment, then we will find the overstrain factors. However, when we use a hinge of AASHTO 4113, that automatically takes a static value of 1.1. That means for every kind of structure it uses a overstrain factor of 1.1. So using AASHTO 4113 we actually cannot portray the actual behavior. So to portray the real life behavior we do a fiber hinge analysis. Now fiber hinge analysis is actually a material level nonlinearity analysis. So we have to provide a we have to provide a hinge length, as this is a kind of distributed plasticity model. So we have to provide a hinge length, and that hinge length has been taken to be 0.5 h, which is a common hinge length used for different structures. So we use 0.5 h, where h stands for the minimum dimension, h stands for the maximum dimension of the element. So with that fiber hinge analysis we calculate the ratio of the maximum moment and the design moment, and finally find the overstrain factor. And we did this study for two different types of piers, one with the single column and with the double column. And for the single column we find that the overstrain factor remains within 1.1. So we say that for single column the overstrain factor 1.1 is okay, but for the double column the value actually goes to 1.22 also. So we propose a overstrain factor of 1.25. And finally what we did is that we actually use this overstrain factor to design the piles. So the force that we designed the piles previously was very higher, but after we use this overstrain factor the force is lower. But still if we do the pushover analysis again, then we can find that even then also no hinge occurs in the piles. So that means we can actually protect the piles from damage even during the maximum constant earthquake. After that I have done some parametric studies. I will just go through this part very fast. Firstly we did a variation of beam seismic zones. So in different kinds of different kinds of response spectrum parameter response spectrum is generated, and then we did the performance analysis. And you know that when we actually change the seismic zones, when we actually go to a higher seismic zone, at that time force is also higher, and that time that capacity is also higher. So that's had been found, and one of the objectives of our study was that to check whether the design guidelines that we are proposing actually provides us a safe structure or not. And so we checked that for all of these cases, the different performance levels, and we found that in every case this is okay. Then we vary the confinement spacing, and we found that when we provide closely spaced reinforcements, our ductility increases. So we find that if we provide the same level of spacing as the other part of the structure, we don't find find much ductility, and the performance level is not satisfied in that case. But after providing 100 millimeter spacing, we find that the performance is evaluated. Then we vary the operational category, which is also okay. After that, we vary the pier height. So we found that when pier height is increased due to the loss of stiffness, the as the time period actually increases, and as time period increases, the elastic seismic elastic response spectrum actually provides a less value. As the time period increases, so the force falls to the right region of this design response spectrum, and as a result less force is required for the design, and also the capacity is lower. Then we vary the column numbers, and in this time also we could see that the performance is okay. Then we varied the cross-sectional shape by keeping the moment of inertia, the I value, okay, the same, and we found that the shape does not actually affect much, although the rectangular piers increase the ductility a little bit, but it is advised to use the circular columns in the reverse. So finally, our main conclusion is that the design guidelines that we have provided can actually provide a safe structure and then can meet the performance objectives, and the piles can be protected if designed by hinging force instead of the elastic force, and that hinging force can be determined using the prescribed overstrain factor that we have already discussed. There are some limitations to our study. First of all, we while calculating the performance, we actually used pushover analysis, and during the pushover analysis some of the soils actually fails during the lateral loading, and as a result we in some cases it can be said that the hinge level is not failing when soil is failing, so some displacement is already occurring when there is no effect on this on the hinge. So as a result, I think we could have done a comparative analysis with the fixed base, and then we could have checked what percentage of the soil, what percentage of displacement the soil is taking, and that could lead to a more better analysis. And also time history analysis could have been used to provide a more insight. Soil modeling could have been done into more sophisticated software. With this, I would like to conclude. Thank you.